Welcome to the Walton Pi. Today you're going to be watching a video of Calculus 1 test review where we will talk about functions and how they are even and odd, what the domain of a function is and how to find it, limits, as well as computing several. We will also talk about the derivative and how to compute it using the definition, as well as what it means for a function to be continuous. We will also talk about the product rule and quotient rule briefly, as well as how to graph functions using different information that you are given. Please enjoy this video, and I hope that you all do well on your tests. Best of luck, and enjoy the video. Okay, welcome to this test review. We are going to be going over the first part of Calculus 1, so single variable calculus. So let's just jump right on in. So let's start by talking about what kind of functions we can have. So if we have functions, like maybe for example we have f of x equals x squared plus 3 divided by x minus 2. For example, this is a valid function. But one of the questions we have to ask about functions is what's going to be the domain of this function. So the domain is anywhere where f is defined. So places where we might have things come up where it's not going to be defined is if we have something like this division that's going on right here. So anytime there's division, what's on the bottom cannot be equal to 0. So anytime that the denominator of a fraction is equal to 0, that is going to not be in the domain. So here our domain is going to be all real numbers except for 2. And the reason for that is if x is equal to 2, the denominator is going to be 0. So some other functions that we might be dealing with might be, for example, if we had a function g of x being the square root of x plus 3. Now, with a square root, what we have to have is we have the inside of the square root function, so this stuff here, that has to be greater than or equal to 0. So here, our domain is going to be the numbers where x plus 3 is greater than or equal to 0, or in other words, where x is greater than or equal to negative 3. That's going to be the domain for this function. The other kind of function that we can have is if we have a function that involves a logarithm. So these are going to be the three main ways that we can't have where there's going to be some problems with the domain. So let's say that we are doing log base 7 of x squared, let's just do x cubed plus 3. So the rule for a logarithm is that this inside piece, that has to be strictly greater than 0. It can't be 0 and it can't be negative. So here our domain is going to be the set of all numbers where x cubed plus 3 is greater than 0, or where x cubed is greater than 0, or in other words where, not where x cubed is bigger than 0, it's where x cubed is bigger than negative 3, or when x is bigger than the cube root of negative 3. Those are going to be the different domains of these different functions. Another type of function that we would have to deal with sometimes is with what are called even and odd functions. So a function is even if f of negative x is equal to f of x. And a function is odd if f of negative x is equal to negative f of positive x. So the reason that these get the names even and odd come from the powers of x. So x squared is an even function, x cubed is an odd function. And so the reason that they get the name even and odd is a reference to x squared, x cubed. X to the fourth is going to be an even function, x to the fifth is an odd function. Any function that is comprised only of x's raised to an odd power is an odd function. Similarly, any function comprised only of x's raised to even powers are going to be an even function. Now, it is possible for a function to be neither even nor odd. For example, x squared plus x. That is not even and it is not odd. And then it's also possible for there to be a function that is both even and odd. However, the only function that is both, that is the function f of x equals 0. So this is the unique one that is both, but there are a whole bunch of functions that are neither. So that's just something to keep in mind. Some other functions that are even and odd that you might come across are sine and cosine. So if you can't figure out which one's which, we can go back to the unit circle and we can try and figure out which one is going to be even and which one's going to be odd. So sine measures the y value. So for some angle here, what we are going to be doing is we're going to see what happens if we look at the negative of the angle as well. So we might notice that the x-coordinates of these 2 points are the same. So because it doesn't matter if we put in a positive angle or a negative angle, since the output of the x-coordinate is the same, that tells us that cosine of x is also going to be an even function. And if we look at the y-coordinates, we notice that the y-coordinate here is the negative of the y-coordinate at the bottom. So that tells us that sine of x is going to be an odd function. So cosine's even, sine is odd, so that tells us that it's not only functions that are comprised of x to odd powers that are odd, but there are other functions that are even and odd as well. So just keep in mind these definitions. It is even if you can put in the negative x value and it gives the same output. It is odd if putting in the negative x value gives you the negative of the original output. And keep in mind it is possible for something to be neither even nor odd, as well as being both. Speaking of sine and cosine, let's go through some. Let's go through a couple different properties of sines and cosines. So you might remember that if we have some triangle like this, and here's our angle theta, that if we label these different sides, so we have, this is the hypotenuse, this is the opposite side, and this is the adjacent side, we might remember that sine of theta, well, if you remember this acronym, SOHCAHTOA, this is a way to remember it. If you don't remember this, you can just memorize the definitions. But sine is going to be opposite over hypotenuse. Cosine of theta is going to be adjacent over hypotenuse. And then tangent is going to be opposite over adjacent. And so using these, we can be able to write down a few formulas that we can use to be able to figure out the other 3 trig functions. So the other ones are going to be secant of theta, cosecant of theta, and cotangent of theta. Well, secant is 1 over cosine of theta, cosecant is 1 over sine of theta, and then cotangent is 1 over tangent of theta. So if you can remember that, that's going to be able to help you figure out all of the different things that you would need. Now, some problems that you might come across are things like this, where we have what is tangent of inverse cosine of x? Well, that's going to be a little bit tricky to figure out unless we draw out a triangle. So inverse cosine of x, that is asking for what angle theta satisfies cosine of theta equals x. That is interchangeable with this cosine inverse of x. We are trying to figure out what value of theta is going to satisfy that. So if we draw this angle theta, and then we remember that cosine is adjacent over hypotenuse, we just need that ratio to equal x. Now we can always write x as x over 1, so let's just make the hypotenuse 1 and the adjacent side x. In order to figure out what tangent of theta is, we also need to know what is the opposite side. So what we can do is we can use the Pythagorean theorem to figure out what is that side going to be. So all we know is it's equal to some value a, and the Pythagorean theorem says that we get a squared plus b squared, in this case x, so a squared plus x squared equals 1 squared. So a squared plus x squared equals 1, which tells us that a squared equals 1 minus x squared. So a is the square root of 1 minus x squared. So we can put that up here. 1 minus x squared. And now we can calculate any of the trig functions that we need. So tangent of theta, that's just opposite over adjacent. So our opposite side is the square root of 1 minus x squared. Adjacent is x. So that tells us that tangent of our theta is the square root of 1 minus x squared all over x. So that tells us that tangent of inverse cosine of x is equal to the square root of 1 minus x squared all over x. Now you can do the same thing for any others. Like you could do sine of inverse tangent of x. Actually, let's do that one because it's going to be a slightly different setup. So we have our triangle, we have our angle theta, and we are trying to figure out what is sine of inverse tangent of x. Well, inverse tangent of x, that is opposite over adjacent. So instead of having the hypotenuse be 1, we want opposite over adjacent to be equal to 1. Or not equal to 1, equal to x. So opposite x adjacent 1, then the Pythagorean theorem tells us that this side is going to be 1 plus x squared under a square root. And so now if we're looking at the sine of that angle, sine is opposite over hypotenuse, so that tells us that sine of theta is going to be x over the square root of 1 plus x squared. So that tells us that sine of the inverse tangent of x is equal to x over the square root of 1 plus x squared. And you can do this for any of the other ones that you have. Just make sure that you are making the appropriate ratio, x or whatever variable you're needing it to be. Let's see, what should we do next? Let's talk about, let's just go back to trying to figure out the volumes of different problems depending on the setup. So let's say that we are given some rectangular box, and let's just say that we are then told to cut out these corners in a square, so each of these sides are x. And once we've done this, we want to figure out what's the volume of the box going to be, and what's the domain and range. We need lengths of these overall sides. Let's say that this side is 30 and this side is 15. Well, let's try and figure out how we can find the volume of the box. Well, once we fold it up, we are going to have these sorts of lines are going to be where the bottom of the box is, and so we are going to get a box looks like this, and then it's going to have a height of x. But the question is, what's going to be these two sides? Well, this side, of course, so this side here, that's going to correspond to this length. And that is going to be the full length 30 minus 2 of these x's. So that's going to be 30 minus 2x, and then similarly, this side is going to be 15 minus 2x. So the volume of the box is going to be x times 30 minus 2x times 15 minus 2x. Now, just looking at the formula, we might say, oh, the domain is going to be everything. But if we did that, we would have neglected the fact that we are dealing with a real-world problem, which means that not all x values make sense. For example, we could find the volume, theoretically, of the box if x was 20, but if x is 20, then these little boxes that we're cutting out are bigger than one of the sides, and so that doesn't make any sense. So here, because we are dealing with a real-world situation, and a box with a side of negative length doesn't make any sense, that tells us that each of these sides has to always be bigger than 0. So our restrictions are going to be x is bigger than 0, 30 minus 2x is bigger than 0, and 15 minus 2x is bigger. Those are going to be our restrictions that we have to deal with. From here, what we can do is we can try and figure out what are going to be the values that make this true. So let's just solve each of these in terms of x. So the first one is pretty straightforward. It's just already x is bigger than 0. The second one, we can add 2x to both sides. So we get 30 is bigger than 2x. So we get 15 is bigger than x. And then the last one is going to be very similar. So 15 is greater than 2x. So that means that 7.5 is bigger than x. And so we need to find a value of x that satisfies, or all values of x that satisfy all of these. And by looking at it, we can see it's going to be these two combined. So that tells us that our domain is going to have to be 0 is less than x is less than 7.5. And those are the values of the domain of our function. Let's see. Let's quickly talk about asymptotes and wholes of functions. So let's say that we are dealing with a function f of x is equal to x minus 2, x plus 3 squared, all over x plus 1 squared x minus 2. So our domain of the function is going to be everywhere where the denominator is not 0. So the domain is going to just be x cannot be negative 1, x cannot be 2. Now for these values, one of the questions is, at these points, what is the behavior of the function? There's two kinds of situations. We could have an asymptote, which could look like that, or the other one. Or we could have a hole where it's kind of just, we took a point and just removed it from there. So the question is, what kind of discontinuity is it? Well, if we can cancel them out, so here we have an x minus 2 that can cancel, that tells us that x minus 2 is a hole. If it completely cancels from the denominator, then it's going to be a hole. However, let's say that we modified the function just a little bit, so it was also times an x plus 3. So that would include x cannot be negative 3 to our domain. Here, this x plus 3 does cancel from the bottom, and because it cancels completely, it would be a hole. But if we modified it so it would be a cubed on the bottom, when we canceled it, the squared would cancel with most of this, and it would not cancel completely. So because it doesn't cancel completely, this is not going to be a hole. Instead, anything that doesn't cancel completely is going to be one of these two asymptotes. So the way that you can figure it out is if it cancels completely, it's a whole, otherwise it's one of these asymptotes. And so that's the main thing to deal with when you're talking about asymptotes or wholes. Let's see. Let's talk about limits now. There we go. Okay, so when we have a limit and we are dealing with maybe like x approaches 3 of, oops. Okay, let's say we are doing, instead of that one, we are doing the limit as x approaches 7 of square root of x plus 2 minus 3 all over x minus 7. Now, because we are dealing with this as x approaches 7, on the denominator, it's going to be a 0, which is why we can't evaluate this at the point. Other limits, such as the limit as x approaches 2 of x squared plus 3, here we are able to evaluate it directly. It's continuous at that point, which means we don't have to do anything special. We're able to just plug this in. So this limit is just going to be 2 squared plus 3, or 7. However, in this first limit, we can't do that. If we were to try, it would cause problems because we would get a division by 0. And so that's where we have to do some cleverness to try and figure out how might we avoid that sort of situation. So let's look at this limit to see what might we be able to do. Now, a common thing anytime you see a square root with addition in either the numerator or the denominator is to try multiplying the entire fraction by the conjugate. What's the conjugate? Well, it's multiply the top and bottom by the exact same thing, except you change this addition or subtraction to the other one. So because it was a minus 3, we changed it to a plus 3. So we're going to multiply that by the top and bottom. Why are we doing this? Well, if we expand out the top, you're going to see why that works out so nicely. It turns out that when we do that, it's going to simplify the top to get rid of the square roots from the top. So what we get is we are going to get x plus 2 minus 9. That's what the entire top expands out to. If you don't believe me, give it a shot on your own time, but if you expand this multiplication out, you are going to get x plus 2 minus 9. And then on the denominator, we are going to have x minus 7 square root of x plus 2 plus 3. Well, if we just simplify the top, that becomes the limit as x goes to 7 of x minus 7 over x minus 7 times the square root of x plus 2 plus 3. Now, because it's a limit, we can cancel. If we were doing something where this was not a limit, we would not be able to cancel, because canceling is eliminating 7 from being a whole. And so that's what we have to be careful with, is that we are only allowed to cancel terms from the top and bottom if we are in a limit. So that is something to pay attention to. So on the top we are left with a 1, and now if we plug in x equals 7, we don't run into a problem. So what we are going to get is we get the limit as x goes to 7 of 1 over the square root of x plus 2 plus 3. We are able to just plug in x equals 7 here, so we get 1 over square root of 7 plus 2 plus 3, 1 over 3 plus 3, so this is a 1 over 6. So that's how we're able to do different things with limits. Other situations that we might run into are anytime we are asked to find the derivative by the definition. Because the derivative of a function is given to us in terms of a derivative. So let's find the derivative of f of x equals 1 over x plus 1. If we want to find this derivative, we need to use the definition of the derivative. So that is f prime of x is equal to the limit as h approaches 0 of f of x plus h minus f of x all over h. So let's just plug in the different things that we have into this limit. So this is going to be the limit as h goes to 0 of 1 over, x plus h plus 1 minus 1 over x all over h. Well, let's just combine the two fractions on the top. The way we're going to have to do that is going to be through getting a common denominator. 1 over x plus 1. That would be an important piece. But we're going to get a common denominator. So that is going to be the limit as h goes to 0 of x plus 1 over x plus 1 times x plus h plus 1 minus x plus h plus 1 all over x plus 1, x plus h plus 1 all over h. Now that we have the common denominator, we can combine those two together. So we get the limit as h goes to 0. Again, everything's all going to be over h. We get x plus 1, x plus h plus 1, and then the top is going to be x plus 1 minus x minus h minus 1. So some of these will cancel, so x minus x, 1 minus 1, and all we're left with is a negative h on the top, and this negative h can cancel to become a negative 1 with that h on the denominator. So this is now the limit as h goes to 0 of negative 1 over x plus 1, x plus h plus 1, and this is going to be a negative 1 over x plus 1 times x plus 0 plus 1. So this is going to be a negative 1 over x plus 1 squared. And so that's how we would be able to be using the definition of the derivative. Other times you can be able to use the nice properties that you've proven. So to recap some of those properties, we have the derivative of x raised to the nth power. That's going to be n x to the n minus 1. The derivative of e to the x, that's just going to be e to the x. We have, let's see, what are the other ones that you've talked about? You might have covered the derivative of a constant to the x. That's going to be the natural log of the constant times a to the x. And then you probably will have talked about the product rule and the quotient rule. So the product rule, this is for if you are taking like some big function f is equal to like f of x times g of x. So the derivative of the product is going to follow this. It's the first function times the derivative of the second function plus the derivative of the first function times the second function. And then we also have what's called the quotient rule. So there's the product rule. The quotient rule is similar except it is for if f is equal to little f of x over little g of x. And here, the quotient rule is going to be f prime is going to be the bottom, so low d high minus high d low all over the denominator squared. So there's a few different mnemonic devices I've heard. I've heard people say a poem like it's low d high minus high d low over low low. I've also heard people have a little song like where they've put that to a tune. Other people have said low d high minus high d low, square the bottom and off you go to make it a little rhyming couplet. But that is what the quotient rule is going to be. Let's see. What other things should I go over with you? We can go over like finding inverse functions. So let's say that we are dealing with the function y equals x plus 1 all over 2x plus 1. And we want to find the inverse function of this. Well, the way that you can find the inverse function is currently we have it solved for y. To find the inverse function, we want to solve for x. So we want to get x equals something in terms of y. So let's just try and figure out how might we solve this to get it to reduce the complexity of this problem. Well, one thing we might do might be to try and flip the fraction. So we might want to, instead of be dealing with this, deal with 2x plus 1 over x plus 1. And so that's going to be equal to 1 over y. The next thing we can do is we can see if there's a way to simplify this fraction to be able to rewrite that a little bit simpler. So we have a 2x on the top and just an x on the bottom. So let's see if we can rewrite the top so it's just 2 times the denominator. If we were to do that though, that would need to be a 2x plus 2 over x plus 1, which is not quite what we have. So what we can do is we can say, well, we want that piece, but then we need to subtract off a 1 over x plus 1. So it's still equal to the 1 over y. Now this 2x plus 2 all over x plus 1, that is really just equal to 2. So we have 2 minus 1 over x plus 1 is equal to 1 over y. Now since we're trying to solve for x, let's take that and just try and isolate the x by itself. So if we add the 1 over x plus 1 to the other side and subtract off the 1 minus y, we get 2 minus 1 over y equals 1 over x plus 1. So if we flip the fraction again, that gives us x plus 1 equals 1 over 2 minus 1 over y. Let's simplify the other side so we don't have a fraction inside a fraction. So let's multiply the top and bottom of this other fraction by y over y. That's going to give us y over 2y minus 1 is equal to x plus 1, which tells us that we can just write x equals y over 2y minus 1 minus 1. And that is our inverse function. We could check this by plugging in different values of x and y and see if they go back and forth, but that should be the inverse function. Let's see. We should talk about continuity. So, a function is continuous at a point A if f of A is equal to the limit as x approaches A of f of x. So what that's saying is that's saying if we have some curve that's doing like this, and if we're approaching the point A, right here, the value of the function is f of a. And so as we approach that value, as x approaches a, the value of the function should approach that point too. So this is an example of a continuous function. However, we might have a function that looks a bit like this. Right here, that might be the value of f of a, but then this point right here, that's the limit as x approaches a of f of x. So because those are not equal, this function that I just drew is not going to be continuous. Some nice properties are that if a function is differentiable, that implies it's continuous. So if f prime of a exists, then f is continuous at a. That's a nice property that you can use. However, the inverse does not, or the reverse direction does not exist. For example, the graph f of x equals the absolute value of x. This is a continuous function, but it is discontinuous down here at this corner. It's discontinuous. The derivative does not exist at that cusp or a corner. But then we can use this sort of idea to solve these sorts of problems that you might sometimes be asked, where you're given a function like f of x is equal to, and then they give you this piecewise function. So if f of x is equal to, let's say, x minus 1, 0, and then x minus 2, where this happens if x is less than 1, 1 is less than or equal to x, less than or equal to 4, and then x is bigger than 4, we might be asked, where is this continuous? Or specifically, or an easier problem might be, where is this discontinuous? So there's going to be a couple spots where it could be discontinuous. That's going to be where it transitions from one definition to another. Because x minus 1 is a continuous function, 0 is a continuous function, and x minus 2 is a continuous function. So our only possibilities are at these points 1 and 4, where it switches from one function to the other. The way that you can check if it's discontinuous is you can see if, for example, the graph x minus 1, if that is equal to the graph 0, we can figure out, do they both approach the same point at x equals 1? Well, as we approach x equals 1 on this side, from the x minus 1 side, that's going to 0. But then that's the same value we get as we approach from this side. It's also going to be 0. So that tells us that this is going to be continuous at x equals 1, because the limit from both sides is 0, and that's the value of the function at x equals 1. The next question is if we have the same thing when we are dealing with x minus 2. So x minus 2 approaching x equals 4. From this side, that's going to the value of 2. But from this side, it's going to the value of 0. So what we get is we get a jump. The graph of this is going to look like this. And so we see that it's going to be discontinuous right here, but it's continuous at the other point. So there's going to be a discontinuity, and specifically a jump discontinuity at x equals 4. Let's see, what other things are there to talk about? We got the squeeze theorem that we can use. So let's say that the idea behind the squeeze theorem says that maybe you have some function that's doing really weird behavior and you just don't really know what it's doing anywhere. But we do know for a fact that there is this function that is always smaller than it, and there is another function that is always bigger than it that does something like this. And both of those functions, we know exactly what they do. And so if they meet at a point, then that means that the limit of our inside function has been squeezed to force to match that one. Now, this graph is a little bit hard to visualize, so let's just redraw it to make it a slightly easier one to do. One of the classic examples of this is going to be the function, what is the limit of f of x equaling x squared sine of 1 over x. What is the limit as x approaches 0 of f of x? Well, as x goes to 0, sine of 1 over x, that's going towards sine of infinity, or sine of negative infinity. And so that's just going to be oscillating up and down really, really fast. And so we don't know where sine of 1 over x is going to be. In fact, the limit doesn't exist if we were to eliminate this x squared term. However, that x squared term gives us a way that we can be able to use the squeeze theorem to solve this. So because sine of theta is always between 1 and negative 1, we can say that that means that x squared sine of 1 over x, that is always less than or equal to 1 x squared, and is always greater than or equal to negative x squared. Which means if we can show that the limit, so the squeeze theorem tells us that that means that the limit as x goes to 0 of negative x squared is less than or equal to the limit as x goes to 0 of f of x is less than or equal to the limit as x goes to 0 of x squared. Well, the limit as x goes to 0 of x squared is 0, and the limit as x goes to 0 of negative x squared is 0 as well. So the limit of f of x has been forced to be between 0 and 0, which tells us that this is also equal to 0. And so that's how you can use the squeeze theorem to help you solve these sorts of problems. If you have a function that you know sort of the behavior, like you can limit the behavior on the top and bottom, and then the other part gives you a way to modify it so it can be squeezed between two values, so that on the top it approaches like this, and on the bottom it approaches like this, but then on the inside it's just doing this really weird behavior that you can't really describe because it's just oscillating up and down infinitely fast. We still know that the limit as it goes to the center is still going to go to 0. And that's the power of the squeeze theorem. Let's see, what else should we talk about? We can talk about how you can use the product rule and quotient rule just from looking at a graph. So let's say that we have this sort of situation. So 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And then let's say that this top is going to be oops, that needs a bit more curve to it. Alright, so any point that I am highlighting is exactly on an integer point, and then I need a few more points. 6, 7, 8, 9, 10. And so then this is going to just go down 1 every 2. So let's say that this is f of x. And then let's say that this perfect, they intersect. Alright, and let's say that this is g of x. Let's try and figure out what is, so if f is equal to g of x times f of x, we want to figure out what is f prime of 2. Well, we know f prime of 2 from the product rule is going to be first times the derivative of the second, so g of 2 times the derivative of the second at 2, plus the second times the derivative of the first, so g prime of 2 times f of 2. All we need now is we just need to know what are these different values at those different points. Well, g of 2 is going to be this point right here, so g of 2 is 2. And then f prime of 2 is the slope of f at this point. And that is just going to be this horizontal tangent, so the slope is going to be 0. G prime of 2, that's the slope at this point here, and that's the same as the slope of g of x, which is a slope of 1/2. Because it rises 1 every 2, and then f of 2, that is the value of the function here, and that is going to be a 1. So that tells us that f prime of 2 is going to be a 1/2. And so you can use your graph to be able to figure out those different values. Let's see what to cover now. Okay. Similarly, we might be asked to graph a function given different conditions. So let's say that we are given -1, 0, 1, 2, 3, 4, 1, 2, 3. Is that enough? No. Alright. Doubling my scale. Okay. Actually, let's just make it a bit more normal. Alright. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. -1, -2, -3, -4, -5. 1, 2, 3, 4, 5, 6. Okay. So let's just write down a bunch of conditions that we then want this graph to have to satisfy. So we want this graph to satisfy the following. We want f of 0 equal to 3. We want the limit as x approaches 0 from the left of f of x to be 4. We want the limit as x approaches 0 from the right of f of x. We want that to be 2. We want f prime at 3 to be 2. We want the limit as x approaches 4 of f of x to be infinity. And then two more conditions. We want the limit as x approaches infinity of f of x to be 3, and we want the limit as x approaches infinity, or negative infinity, as x approaches negative infinity of f of x, we want that to be -2. So let's figure out how might we be able to graph all of these different things. Well, the first thing that we can use is we need the value of f at 0 to be 3. So that means we need to at least have that point be defined. We also need the limit as x approaches 0 from the left to be 4. So that means that from this side, we need it to somehow approach 4. So we need it to connect up like that, and then from the right, it needs to approach 2. So it's going to need to do something like that. We also need the slope of f at 3 to be about 2. So the slope of 2, that's going to be about a slope like that. So if we're just sketching, that's about a slope of 2. So we just need it at 3. So let's go straight up. We need the slope of this to match that at that point. And then we are told that as x approaches 4, it goes towards infinity. So we have this vertical asymptote, and this needs to just go straight up there. Now, since it's saying it's as x approaches 4, not just as x approaches 4 from the left, we also need it to approach infinity from the other side. So far what we've done is we've accomplished this piece, this piece, this piece. F prime of 3 is 2, and the limit as x approaches 4 is infinity. The last thing is we need the limit of f of x as x approaches infinity to be 3. So that means we need this to probably stabilize about like this. So it's going to stabilize like that. And then the other thing is we need, as x approaches negative infinity, it to go towards negative 2. So something like that would work. So this is one valid function that describes exactly these conditions that we had. Just go through the conditions one at a time and figure out what you need to satisfy in order for it to hold. Let's see, what else might we use? Okay. The last thing I can think of is to just go through some examples of some limits with you all. So, let's say that we are trying to find the limit as t approaches 0 of 6 over t squared plus 3t minus 2 over t. Well, the first thing we would probably want to do is try and see if we can combine those two fractions together. So let's get a common denominator. So limit as t goes to 0 of 6 over, t squared plus 3t minus 2 over t, multiply the top and bottom by t plus 3. That's going to give us a common denominator. So it's now the limit as t goes to 0 of 6 minus 2t minus 6 all over t squared plus 3t. That's the limit as t goes to 0 of negative 2t over t times t plus 3. The t's can cancel. That's the limit as t goes to 0 of negative 2 over t plus 3. As t goes to 0, that's just going to be a negative 2 over 3. So there's our limit. Let's see, what else might we do? Okay. The next one is going to be the limit as x approaches 2 of 2x minus 4 over the absolute value of x minus 2. Now this one, we might want to be a little bit careful with. Anytime there's an absolute value, because it does this, that can cause some problems. So as soon as I see the absolute value, I am skeptical that it might actually not exist. So let's look to see what happens on either side. So let's look at the limit as x approaches 2 from the left of 2x minus 4 over absolute value of x minus 2. Remember, absolute value of x minus 2, that is equal to one of two things. It's either x minus 2 if x is greater than 2, or it's negative x plus 2 if x, and that is if x is less than or equal to 2. So if x is less than or equal to 2, we can replace x minus 2 with negative x plus 2. This is equal to the limit as x approaches 2 from the left of 2x minus 4 over negative x plus 2 equals negative 2, limit as x approaches 2 from the left of negative 2 times negative x plus 2 all over negative x plus 2 those cancel, this is equal to negative 2. However, if we look at the limit as x approaches 2 from the right of 2x minus 4 over absolute value of x minus 2, well, here we can replace the absolute value of x minus 2 with just x minus 2, because as we approach it from the right, x is always greater than 2. So that's going to be the limit as x approaches 2 from the right of 2 times x minus 2 all over x minus 2. And so this is equal to positive 2. Because these two values are not the same, this tells us that the limit does not exist. So because the limit does not exist, that tells us that we can't actually evaluate it, because it goes to two different values on two different sides. I hope that this was helpful. I don't have any other material to go over with you, so I hope that you are all able to do well on your test, and I wish you all the best of luck. I hope you all enjoyed that video. Feel free to check out some of my other videos. I will be making calculus videos very soon, so please subscribe so that you don't miss any of those. I will be going through all of single variable calculus in the order that I think it should be taught. And I hope that you will all stay tuned to be able to go through that and learn it with me. I hope you all have a wonderful rest of your day, and good luck with the rest of your math.